This video is going to go through a few examples, three to be exact, of questions that you will come across as you look at interpreting reaction mechanisms. So no point in delaying, let's get stuck into them. So here's the first example, and as you can see from this proposed mechanism, it's a three-step process, and it does have some information about each of those different reactions in this mechanism. Slow for the first one, fast and fast for the second one. As I'm sure you realize, that slow is a big hint for us. So first thing is, what is the balanced chemical equation for the reaction that occurs by this mechanism? Well, that's the first question. We're going to actually answer the second one first, identify any reaction intermediates, because once we find the intermediates, we see what is left, what is not an intermediate. So if you remember what a reaction intermediate was, it is those species that get formed in a mechanism, in a reaction, but are then used as a product. So I'm looking here in the first slow step, nitrogen monoxide yields dinitrogen or dinitrogen dioxide. And so it's then used in the next step. So N2O2 is actually a reaction intermediate. Formed in step 1, used in step 2. And what's the other intermediate? There's one other, and here it is here, N2O. Formed in the second step, used as a reactant in the third step. So there is none of it left. So N2O2 and N2O are the reaction intermediates. So now we can fairly easily identify what's left, NO, 2 moles of hydrogen, 2 different reactions, 2 moles of water, and N2. So here's our overall balanced chemical equation. 2 nitrogen monoxide plus 2 hydrogen yield nitrogen gas plus 2 water. So there's the overall balanced chemical equation and intermediates. You should always be able to generate the balanced chemical equation. What is the molecularity of each step and of the net reaction? If you remember what molecularity is, that's this idea of collision. So how many collisions are required, or what's the type of collision that is required to generate the products in each step of the mechanism. And so molecularity, if you look here, we have 2 moles of nitrogen monoxide in the first step. So 2 moles of nitrogen monoxide implies a bimolecular process. Okay, so 2 particles collide, bimolecular. Well, steps 2 and 3 are also bimolecular. Here's 1 mole of N2O2 plus 1 mole of hydrogen, that's bimolecular, and N2O plus H2. So all steps in the mechanism are bimolecular. How about the overall reaction? Well, we have 2 moles of nitrogen monoxide plus 2 moles of hydrogen. So overall reaction is, quadmolecular. I don't know what the term is. So let's just say is a 4-particle collision. 4-particle process. And again, you should hopefully recognize fairly quickly that, remember, that 4-particle process, 4 particles colliding with sufficient energy, with appropriate orientation, and coming together so all those 4 different electron clouds interact at exactly the same time is highly unlikely. Remember, those elementary processes are unimolecular, bimolecular, or trimolecular, but a 4-particle process is not considered elementary. So this is why we probably realize that this overall reaction doesn't occur as written. So again, that's the whole point of mechanisms. A 4-particle collision is highly unlikely. There must be some other process, and this is the proposed mechanism for that process. So anyways, molecularity, you should be able to pick that up from the individual steps and from an overall reaction. All right, let's carry on. So what is the rate law for this mechanism? Well, again, the rate law stems from the slowest step, and our slowest step here is step 1. So this is the rate determining step. and we've already ascertained that it's an elementary process, bimolecular, so that works. And so if the mechanism has an elementary process that is rate determining, you know the rate law. So R is going to equal K times the concentration of nitrogen monoxide squared. So there's the rate law for the mechanism, generated from the rate determining step. So what happens if the rate of reaction is, or to the rate of reaction if the concentration of nitrogen monoxide is doubled? Well, if you double concentration of NO, rate increases fourfold. And again, that's pretty easy to see because basically what we've done is 2 squared. What will happen to the rate of reaction if N2O2 is doubled? Well, how do we decide this? Well, let's look up here to our rate law. No N2O2 in rate law means that there will be no change in the rate of reaction if we double the concentration of dinitrogen dioxide. Okay, if it's not in the rate law, it does not affect the rate of reaction. Okay, so those are a few questions you need to be able to answer. Let's look at another example. So this is a little different. Following potential energy diagram for a proposed mechanism. As I did mention before, you can see mechanisms written as potential energy diagrams. So what is the overall activation energy? Well, that's back to thermochemistry, thermodynamics. So overall activation energy, here's our reactants. We have to apply some energy. We have to apply this much energy. Okay, so that's overall activation energy. And it is 60 kilojoules. So just reading off the graph. What is the rate determining step for the mechanism? Well, the rate determining step is this step. The rate determining step, remember, is the smallest, or the step with the the highest overall activation energy. And so in this case, that's from the reactants to V. So reactants to V is the rate determining step, and the activation energy for the rate determining step is a little different. So it's from there down to there. So that's EA for rate step. And so that is actually 50 kilojoules. Okay, so 50 kilojoules for the rate determining step. You require an extra 10 kilojoules just to get over that little hump of X. But remember, that activation energy from V through to X to convert reactants V to X will be only, it's actually about 25 kilojoules. Okay, so let's carry on. So a couple other things. Is this reaction exothermic or endothermic? Well, we just have to look at reactants and products there and the energy associated with these. And so reactants energetically more higher, so less stable than the products. So therefore, this is an exothermic process. What is the delta H for this reaction? Well, there's the delta H. There's the amount of energy released. So delta H equals minus 35 kilojoules. Which letters represent activated complexes? Now, if you remember what an activated complex is that quasi-molecular species that is sort of originates from the process of bonds forming and bonds breaking. So it's this sort of intermediate between the reactants and the products. So it's not reactants, the bonds haven't fully broken, but it's not products, the new bonds haven't fully formed. So activated complexes occur at these peaks in the potential energy diagram. So those are the peaks. So the letters that represent activated complexes are V, X, and Z. Which letters represent reaction intermediates? Well, again, intermediates, as we saw from the last example, those are those species that get formed as a process part of a reaction and then get used up, and so do not appear in an overall equation. So we can look at reaction intermediates as W and Y, and this is how you would come across W. So what you have for W is you have reactants yield W, but then W immediately decomposes or breaks down to form Y. So W is not going to be part of the overall equation, so it's a reaction intermediate. So that's the second sample. How about the last one? So the last example, again, a possible mechanism of decomposition of hydrogen peroxide, H2O2, is shown here. Experiments reveal a rate law for the mechanism is first order. Demonstrate with brief explanations that the accepted mechanism shown is reasonable. And so this is kind of important here. The accepted mechanism is reasonable, and explanations that associated with that. And so this is kind of what we look at here. Demonstrate with brief explanations implies that we have to mention molecularity of the different steps. We have to generate a plausible balanced chemical equation from the mechanism, and we need to be able to generate a rate law consistent with experiments. And so we can generate the rate law pretty quickly because we know the rate determining step. The slow step is the rate determining step. That's step 1. And so a rate law R equals K, concentration of hydrogen peroxide, raised to the power of 1. So there's our rate law, which is acceptable because it says the rate law for the mechanism is first order. That's a first order reaction, so that elementary process. In terms of generating a plausible balanced chemical equation, well, we know it's a decomposition, so what we have to do is look for intermediates. So here's H2O2. Well, it's on both sides as reactants in these two steps, so that's not going anywhere. Here we have hydroxide. We have 2 moles of OH generated. Well, there's 1, 2 used up. So hydroxide is an intermediate. What else do we have? Water. Well, it's there. We have this HO2 radical as a product, as a reactant in step 3. So that's a reaction intermediate. And so that leaves 2 moles of hydrogen peroxide, 2 moles of water, mole of oxygen. So our overall equation is 2H2O2 yields 2H2O plus O2. And it should come out balanced, and it does come out balanced. 4 hydrogens, 4 oxygens, 2 plus 2, 4 oxygens. So we have generated a plausible, balanced chemical equation for that. And in terms of is this mechanism reasonable? In terms of molecularity, all steps are elementary processes, so could very likely occur as written. So the mechanism is probably feasible. It's possible. Whoops. Okay, so that's sort of what you need to be able to manage when you want to try to explain whether a mechanism is possible. You have to generate a balanced chemical equation. That is a decomposition reaction, single reactant yielding 2 products. We have a rate law consistent with experimental data. Here's our experimental data, the slow step. And the proposed mechanism involves only elementary processes. So that all seems reasonable. Just a couple other things then. So rate law for the mechanism. Well, we do have to go back to that slow step, and there it is. So the rate law, as we already know, is K. Our rate is equal to the rate constant K times concentration of hydrogen peroxide. So a rate law comes from the slow step. In terms of reaction order with respect to hydrogen peroxide, first order, right? Because there's a 1 there. What is the reaction with respect to HO2 radical? Well, it's not in the rate law, so it's 0th order. And so basically it doesn't matter. Concentration of HO2 radical would not affect the rate of reaction. What will happen to the rate of reaction if the concentration of hydroxide is doubled? Nothing. And why is it nothing? Because OH minus is not part of the rate law. Okay, not in the rate law, does not affect rate. It's 0th order as well. Concentration of hydroxide is 0th order. What will happen to the rate of reaction if the concentration of hydrogen peroxide is doubled? Rate doubles. If concentration is doubled. And again, that's because you have a doubling concentration raised to the power of 1, 2. And so that briefly goes through a few of the types of questions you're going to have to be able to answer that deal with reaction mechanisms. And so that concludes this video.